Thank you very much for the introduction, Christian. My name is Thorsten Höffler from ETH Zurich, and today I'm going to talk about FPGAs, but actually FPGAs in the context of high-performance Python and also CPUs and GPUs. So the HEART' Symposium is focusing on reconfigurable computing, and I really want to put it a little bit into a broader perspective. How do we make reconfigurable computing, but even hardware design, accessible to the broad masses, essentially, so that we can have an arbitrary domain scientist, like for example, a climate scientist, programming devices or programming codes that are eventually running either directly in hardware or on FPGAs, which is also somewhat directly in hardware. So, but let me start with a couple of slides that I've presented many times. So you may want to skip those if you've seen them before. But it's really important to have the motivation with the changing physics of computing. So why do we do this? Why is today the time to consider these hardware, these spatial programming devices? And it's really because the last 40 years in computing have followed a very simple pattern. The very simple pattern was faster and faster and faster devices, faster and faster sequential performance. But here I'm taking a diagram which was designed by Horowitz et al. And I changed it a little bit to also show the move from homogeneous to heterogeneous here at about 2011. Because what happened there is that the sequential performance went down significantly. The frequency of the device went down. The number of cores went up. Of course, the parallel performance and the number of transistors stayed about the same. So this was really due to the fact that Dennard scaling ended and we couldn't just scale our devices faster and faster and faster. So our single core devices. And then even today, Moore's law is ending, and Moore's law is very similar, has a very similar impact. So now we even need to use these transistors more efficiently because the transistor scaling curve, as we see up there, is flattening down, at least if you look at the constant cost per transistor, so the cost per transistor cost. But how did we ride this wave for the last 40 years? Well, it was a success story of materials design, shrinking processes, making transistors smaller and smaller and smaller, and following Dennard's law, or Dennard scaling. So we have actually, just a couple of weeks ago, TSMC and IBM both announced a 1 nanometer process. So it's still going, they still improve the process. However, the problem is that eventually this has to stop, right? So we cannot scale towards zero. I mean, definitely before we hit zero, we will hit some other limit like the atomistic the constraints in our devices. So, but what are the fundamental limits we have here? One of those may be the Landau limit. The Landau limit is the minimal amount of energy required to either remove or create a one and a single bit, so to flip a bit, where we are not really bound by it. We are still a factor of about 100,000 away from the Landau limit today. Maybe it's a little bit less now because we are also pushing that boundary, but it's still a huge gap. What we are bound by today is really the electrical data movement, because communication on chip is going through electrical wires that are etched into silicon. And now the loss of such an electrical wire is proportional to the resistancy, which is a device constant, times the length of the wire, which is fixed because the reticle size is fixed, divided by the cross-section area. And as we shrink these transistors, the cross-section area goes smaller and thus the loss goes higher. So what we need to worry about now is locality, spatial locality, temporal locality, and I want to introduce a third form of locality that I call control locality. So the first two are well documented in that survey that was led by DDEM to talk about trends and data locality abstractions for HPC systems in our context here. But the last one, the control locality, is something that we can explore and exploit with spatial devices. And what does this mean? Well, it really means, somewhat abstractly seen, the difference between data flow architectures and load store architectures. So how does a load store architecture work? Well, we have the design, we have values in memory, we have an ALU, we have registers, we have a control logic, and we have some cache that has usually no semantic meaning but improves performance. And then we have a data path between all of those. But every single time we execute an instruction, the instruction is loaded from memory and then loads the operands into registers. So it keeps doing this. It's often called the tick-tock model because it ticks the instruction and then talks the operands. And this is really how most of today's computers work, like this watch, for example, or the laptop I'm using to talk to you right now. And this is relatively wasteful because all of these elements, all of these instructions and operands need to move through all of these paths pretty far through the chip. And this means we have a relatively high energy consumption. The performance is large because we pipeline and overlap all of that, but we still have a lot of data movement going through the chip. So really utilizing these expensive metal layers. While the static data flow model is very different. The static data flow model still has the operands in memory, of course. But what it does, it lays out the execution itself, so the program itself, in a spatial way. So here we have two adders and a multiplier, and then connects those, of course, with the input operand buffer, so two input operands for each of them, one output operand, and then it has a very customized data path. So now the data is flowing very targeted with minimal control. So the control is only essentially figuring out, is the data available, then add it or multiply it, and then output it to the next one. So extremely limited control. There is no addressing and nothing. Addressing is all encoded in the structure itself. So this data flow model thus leads to very high efficiency. So 1, 2, 3 picojoule per bit, which is already orders of magnitude better, or one order of magnitude, a little bit more than one order of magnitude better in terms of energy consumption than the von Neumann model or the load store model. So this is what I call high control locality, because there's very little control overhead, and on the other side, very low control locality. So for those of you who are familiar with SIMT or vector units, you may now say, well, we get this similar effect from controlling multiple ALUs with the same instruction, which is the principle in SIMT and vector units. Yes, we do, but they still have to access random access memory. And this is expensive. The random access memory in a GPU, for example, or in a CPU is relatively large. And the larger the memory it is, the more energy I consume to just load a fixed size element like 32 bytes or 32 bits even from that memory. So you can see it here for loading 32 bits from an 8 kilobyte memory is 10 picojoule, from a 1 megabyte memory already a factor of 10 more. While in this fixed data path, I'm only addressing the local registers here. So there is no addressing at all, essentially, because that's a fixed register. So here I only need 0.1 picojoule, so a factor of orders of magnitude higher or better in terms of energy consumption. So still GPUs and CPUs have higher vector CPUs. Vectorization and SIMT gets us higher control locality, but still not as high as data flow architectures. Right? So really high performance computing is a data management challenge. So what does this mean? Well, we already know since many of the talks in the DOE that many of us have seen, data movement is the dominant power cost. Many companies already announced communication dominates arithmetic, like NVIDIA in this case. My group has actually written a paper for a machine learning systems conference, the MLSys conference. Data movement is all you need. A case study for a deep learning network, so these transformer networks. We even got an outstanding paper award at this conference for the recognition that really you want to tune data movement. You don't want to focus on the flops. You want to focus on how the data moves through the system. In this case, a GPU, but the similar system applies to better architectures. Even luminaries like Shekhar Borkar and Andrew Chen have more than a decade ago pointed out that this is problematic. So we need to understand how to move the data through the system. We need to really depend on sophisticated software to place computation and data so as to minimize data movement. Right? And now the question is, what is this sophisticated software? How do we program today? Well, to a first approximation, really how we programmed yesterday or last year or 40 years ago. So really that has not changed since a long time. And this is what I would call control-centric programming. So in control-centric programming, we really worry about the operation counts. We worry about data movement at most implicit. But this is how we think about algorithms. So this is quite important. Because the way we design algorithms is do this, then that, and then this. If this is true, then do that, and so on. This is just the human way of sequential thinking, how to design how to design an algorithm. And the parallel algorithms are usually just simple generalizations of those. So how do we now cross the chasm between algorithm design and data movement that we need for the fast execution of these codes? Well, first of all, we have to recognize that the domain scientists, the algorithm designers, they have to remain in control-centric land. Right? So they're not willing to leave this and suddenly think data-centric. Furthermore, the performance engineers, they must live in data-centric land because they must understand how to arrange the data on the chip, on the device, on the spatial computing architecture. And an intermediate representation can be used to link these two lands, and this is exactly our proposal. So we really have both adapt to find a common ground in intermediate representation. And this is what we propose with the Dace framework, or with the general Dace idea, where we have a domain scientist. The domain scientist works in his or her land, really with equations and NumPy and high-level DSLs like TensorFlow, PyTorch, and MATLAB, and then works with an applied scientist that translates these output languages into what we call the stateful data flow graphs, or parametric data flow graphs, which is really an internal representation that is amenable to performance engineers, so to people who really mainly care about the performance of these devices and these codes on these devices. So this is what I illustrate here with the code ninja on top, because that is a person who is relatively highly skilled in the details of the devices and does not really understand the domain. Right? He just understands the data flow, and this is the abstraction that person works with, just looking at the data flow and mapping that data flow ideally to the device. And then, of course, the device mapping is then through a code generator in our framework, so to CPUs, GPUs, or FPGAs, and very specialized to the target device. So typically, what you have is you want to write as little lines as possible as a domain scientist in order to implement your problem. Furthermore, the performance engineer also wants reusable transformations so that the work is not too big, but it can be more because that's a coding expert essentially. But at the end, we are generating thousands of lines of code that is really unmanageable for humans, even expert humans, when we map this to the target device. So this is a very, very low-level interface, very low-level programming if you want the highest possible performance. And you know this yourself from tiling your loops and optimizing your codes and pipelining everything. That generates a lot of code that you don't really want to do manually. So furthermore, the question is, why do we care about Python? Well, first of all, Python is going to be, according to the TIOBE index, the most popular language relatively soon. So the headline is already a couple of weeks ago, June 2021, is about to take the first position on this TIOBE popularity index, so nearly passing C. By the way, we also support C, but this is not part of this talk. But here we really focus on Python as the language of computational science and data sciences, as you can see with the success of PyTorch and TensorFlow and all of these frameworks. So scientific Python is actually really was developed in the scientific computing environment. So NumPy itself was very early on optimized by high-performance computing people from Livermore, for example, trying to make it as fast as possible on their devices, because it is a very productive language for scientists. So many framework exists to make NumPy fast. But now the question is, how do we have a fair comparison between those? Many of you probably know Numba as one of those frameworks, and Numba is an excellent framework to port Python codes to CPUs. So what we did is we designed a NumPy, the so-called NumPy bench, so a small benchmark that draws from implements 51 different small NumPy kernels from 9 different domains, and please add yours. So this is all open source. This is available on GitHub, so we accept pull requests. So if you have additional domains you want to support, let us know or just contribute them directly. And then we compare this, each of these implementations with respect to 2 metrics, performance and productivity. Performance is the obvious one, how fast does it run? Productivity is now, how many lines of code do you have to change in the original NumPy implementation in order to get to the productivity, to get to the output format. And we support currently multiple frameworks, but please, again, it's open source. If your framework is not in the list and you want it to be on the list, please add it as a pull request to the repository. So we have Python, Numba, CuPy, and our own Dace, and of course the NumPy baseline, which is the default that all the codes just work without changes. So we encourage you to do this. For the performance side, we have a pretty nice output visualization, which is too complex to discuss in this talk, but really each column here represents a framework, and each row represents a particular code. The rightmost one is the NumPy framework, where we have the absolute performance in seconds or milliseconds, while the other ones are all relative to the NumPy baseline. The green ones are faster, and the speed up is the number that you can see here, and the red ones are slower, and the slowdown is also the number that you can see here. So for many GPU codes especially, you can see that they actually get slower if you run them through CuPy, because on the GPU, if the code does not parallelize, it doesn't run too well. Dace in this case does not really compile most of those that are not really parallel, because why would you run them on the GPU if they're not parallel? So just to summarize the results, what's quite interesting is if you look at the total, and that's the topmost row, where we look at the different speedups for over NumPy, and you can see all of these frameworks on geometric mean give us a speedup, but Dace is among the fastest. So we get a 13x speedup for the GPU case and a 10x speedup for the CPU case, while NumPy, for example, gets you a 4x speedup for the CPU case on exactly the same architecture. You see the details up there, 16-core Xeon Gold. So now, in the remainder of this talk, I want to explain a little bit how this works and what the magic here is. There's actually no magic, it's just ideas. And also I want to focus on, since we are at the HEART conference keynoting here, I also want to focus on how do we design these things for hardware, for FPGAs as an output. Right? It's all about the internal representation. That's what I mentioned before. So what is our internal representation? What is the trick? Well, the trick is simply that we look at an equation here in this case, where we have x squared plus sine x divided by pi, and we just wrap it into a box for now. And then we determine what the inputs are. Well, this only reads x because pi is a constant, and we determine what the outputs are. In fact, then we forget about the equation itself. The performance engineer does not look at the details of these equations, just looks at the inputs and the outputs, where we have x and y. By the way, we call these inputs and outputs memlets. Furthermore, usually in scientific computing, you have not scalar inputs and outputs, but arrays, because otherwise it's not performance critical if you only have a scalar. So you usually have lots of arrays going to n-1, where n could be in the millions. And we have, of course, a shortcut notation for this rather clumsy way of showing it. And the shortcut notation is what we call a burger. So you can see here the upper end, the upper bun and the lower bun, and this is actually really, technically it's called a map, but the meat in the middle is now the tasklet. And the upper and lower bun, or maps, they limit our iteration space. So here we can see that we iterate from I equals 0 to n, they could be multidimensional, and then the tasklet in the middle is really executing massively parallel, so each iteration is independent in one of those maps, and reading from the input array A and writing to the output array B. So this is somewhat the simplest possible map, just to explain you how the visualizations in the following will actually work. So really that's an iteration space. Every time you see one of those shapes, it's an iteration space of independent iterations. So of course, not all applications can be represented as iteration spaces of independent iterations. So sometimes you have a dependency between those, like for example, the left one here and the right one are two of those independent ones, but there may be a dependency that state 0 has to finish before state 1 is started, because state 0 obviously reads from array A and state 1 writes to array A, so that may be that it's overwriting values. So there is a way to enforce sequential execution, which we call states. So now to just summarize the concepts, this very quick whirlwind overview of what we're actually doing. So we have data containers, which are really just like arrays, NumPy arrays most of the time. We have computation, this is just Python code or transformed code. And then we have data dependencies, which are also the obvious ones, like what data is read where. And then the not so obvious ones is basically the states that introduce sequential order, and the maps that introduce iteration spaces, right? So these are the important concepts for the following. But now back to how do we generate hardware descriptions? So we have this performance engineer who works with these parametric data flow graphs. By the way, this here is a screenshot of our tool, so it's not as pretty as the previous slides, but it's a real example that comes from a NumPy input. So you can see the data flow, you can see iteration spaces here. This is a map up, sorry, I can't go that large, that high. Here is a map, and then there are multiple maps that we are seeing. We are actually also seeing multiple states. So let me use this here. So we are seeing one state up here. It's maybe a little bit dark. We are seeing the main state here and one state down here. So there's a sequential dependency between these three things. But inside each state, as you can see here, this is a pure data flow section. So a state itself is pure data flow. So there is no, there is no dependency that you cannot see. And this is very beneficial because now you can already see how this is a 2D visualization, how you can lay it out on a chip or on an FPGA, for example, because all the data movement is explicit. So we really understand from looking at the picture everything that happens in there. And then we automatically generate this code for CPUs, GPUs, or FPGAs. Again, in this talk, I'm going to focus on the FPGA code generation because of the HEART Symposium. So, but is this code going to be efficient? Well, this is just the code that was generated by the front end from what the domain scientist wrote. So this is, of course, correct code. It is, by the way, each of these SDFGs, as we call them, is the full code. So each of these small tasklets here contains the source code that is necessary to be generated. So I can take one of those SDFGs and generate executable code that will be functionally equivalent to what the Python source code was. Right? So we consider these things full programs, but they have all these explicit data dependencies in here. So the original representation may not be the best suited for FPGAs. This is why the performance engineer works with graph transformations to actually transform these graphs into different shapes. And then I want to show you a little bit of an example how we take this graph on the left, which is a very, very simple case of an XP followed by a dot with 3 input arrays, X, Y, and W, and a temporary value Z, and an output array, which is a scalar result. So what first happens is if we translate this to FPGA, we have to first take the input elements from X, Y, and W, from the arrays on the host, and transform them to, or copy them to FPGA memories. Furthermore, we must have the FPGA memories designed to support on-chip storage. Right? We don't want to go back to the DRAM, so these are essentially block RAM storage. We can also store them in DRAM on the FPGA, but that would be too expensive for this particular small example here, only if they're too large. And then, of course, the output needs to be copied back to the CPU, and this is just this state. So state number 1, copy in, execute. State number 2, state number 3, copy back. You can see there are states involved, and each of those XP and dot functions, they have then their iteration spaces, as we will see in a couple of minutes. So this code will automatically be generated for the FPGA here. So really, really easy. So not many bugs possible even. But now the question is, we have all these memory accesses. Now we actually want to stream them on the FPGA, because as you know, the FPGA is very inefficient in bulk execution. It's really efficient in streaming execution. So for this, we have to, for each of these input arrays, we have to generate small devices that read them from DRAM, like small devices in logic, of course, and input them into our chain. So here we have these 3 things, 3 devices that are, again, these iteration spaces, and they output streaming nodes that are identified by the color here. So then, this is basically the input stream memory from the input. And of course, there are 2 that are the input and 1 is output, right? So we do the same. But the streaming between the operators is very similar. So we now want to make sure that this FPGA Z array, for example, works through streaming. So here we want to connect the input or the output of this XP operator with the input of the dot operator up there. And this, of course, goes element by element by element. So we map this to a particular to a particular unit that is then synchronized through a producer-consumer element by element synchronization on the FPGA. So this is also done automatically, the streaming between the operators and the code generated for this. So now we saw how we can turn a non-streaming code containing of multiple iteration spaces into a fully streamed version for FPGAs, element-wise streamed. And again, the code is automatically generated as an HLS code that we can just compile with any of the tool chains. So talking about the tool chains, we actually support both Vivado HLS as well as Intel's OpenCL toolchain. So one is C++ and the other one is OpenCL C. And you can see they require slightly different pragmas that basically mean the same thing, but unfortunately have slightly different syntax. They also require slightly different intrinsic functions, where you can have shift registers on the Xilinx side and then channels on the Intel side, but essentially they do the same thing. They queue elements that produce a consumer synchronization, and that's basically all. And we can automatically generate from the same input representation both Xilinx and Intel code. And furthermore, you don't need to worry about all this boilerplate code to copy arrays in and out. I've already mentioned this, and even launch the kernels and define the kernels, and all of that stuff is automatically generated. Furthermore, the host device interaction is all automatically generated. You see these copy from host and copy to host things mentioned before. So this is all part of the framework itself. And then last but not least, let's look at the actual source code that you see as a programmer. And here, this is just Python code, right? So we are defining some symbols. We have the make SDFG call where all your user code goes, what the SDFG actually does. So this is the, we are just showing the boilerplate here, which is relatively short. And then we can just work with NumPy arrays. So really, the user code, we just call this as a Python function then, and then we just read from existing NumPy arrays. So relatively simple. So at the end, what we can show is that we can run all Polybench applications directly from NumPy through Xilinx and Intel on the FPGA. Right? So that is pretty nice. We are actually, I believe, the first who can do this. The 30 different small micro benchmarks. We do not support all of NP Bench yet. There are some engineering feats missing in order to support all of it. We are a research program, not a product. But it is relatively good. So you can easily code around these issues. You can actually use it today. Furthermore, we have a GUI to work with these SDFGs. So this is now a screenshot of Microsoft's Visual Studio Code, an open source code editing GUI for C, C++, and Python in our case. So the performance engineer can look at these SDFGs, can transform these SDFGs. You can see on the left side, there are just transformations you can click, like map tiling, state fusion, and this will basically just tile the map for you. And you don't need to worry about the indices, getting them right, or having a ±1 error. So it's really hard to introduce hard bugs in this case. And then on the bottom, you can even instantiate that graph and simulate it for specific sizes. But let me now close this kind of micro benchmarky business, and let me get to something more exciting. So what if we could run a full weather simulation on an FPGA or on a hardware device? If we had RTL code, we could print a chip with the simulation code for a full weather code. So that is somehow was the declared goal of a project that we started in my lab a couple of years ago. So it's still going on. It's a bigger effort, and the goal was to run big parts of Cosmos, so the so-called dynamical core on it, on all kinds of different devices. So we managed, currently it's running on GPUs. So one of my ex-students who now moved on to Google actually formed the basis of the current production code for Meteor Swiss, which later moved to Grid Tools, so was called Stella at the time. So we supported the National Weather Service moving to GPUs for production. And as a side project, we thought, well, couldn't we do this on FPGAs as well? Because now we have all the code in a format that we could basically just merge or transform. And so that's the experiment we are trying. It's not so simple, and I will talk about the details in a little bit. But the idea is now we take these complex weather codes, and these are now non-trivial stencils, these are quite complex stencils. This is one of the smallest ones here. And we want to pipeline them in a fine-grained manner on this spatial computing architecture, in brackets FPGAs or any other spatial computing architecture like CGRAs or even hardware. And we want to really make sure that all of this just streams through the device that you can see overlaid here. So to have a full spatial programming. And in the fully pipelined way, we can then stream this all in parallel and mainly use streaming parallelism in order to implement this. And all of this coming from a high-level scientific DSL that the climate scientist can change once a month. Because this is how often many of these codes actually change. So really, maybe printing a chip is not too realistic, but reconfiguring an FPGA or a CGRA may be very realistic in this case. So, but this also makes it unrealistic, by the way, to rewrite that code in C. Because these climate scientists, they are not going to write your code in C or OpenCL or their code. No, they want to work in a productive environment, which is MATLAB or Python. And thus we have to connect to them. We cannot expect as a community that they're going to take our crazy low-level programming models and will work with them. That is quite a tough expectation, and we will lose many scientists if we actually make this assumption. So, but let me first go a little bit more into detail of what a stencil operation is. I'm assuming many of you know. I'm going to do this very quickly. Stencil operation is usually an operation that iterates over a k-dimensional field. Here we can see 2 dimensions going from I equals 1 to n and going from j equals 1 to m. And here we can see the 2 fields I'm showing here, A and B. These are the input fields. So the input field A is essentially read on the, for each computed output, it reads the northern element and the southern element, and for the input field B, for each computed output, we are reading the eastern element and the western element. So this is a typical stencil. You usually evaluate this for each of these grid points here, point by point by point, and then need to always read the input fields, so A and B are input fields, at this particular location, and then again, A in north and south and B in east and west, and then you can compute the result and the equation you see on the left side. So this is what stencil programs are. So, and oh no, actually this is what a single stencil is. A stencil program is now a directed acyclic graph of many of these stencils that consume many of these fields. So here we see one that consumes A and B and produces C, but this can be arbitrarily complicated, as we will see in a couple of minutes. So the stencil flow idea and prototype is really starting from a way to express these stencils that are then compiled to the stencil DAG. And the way to express these stencils is currently in a JSON-based front end. It is still not usable by a domain scientist because you can see this. This is kind of a specification that gives us all the necessary ingredients of the stencil itself, but it's still written in a format that is not super convenient for the climate scientist. But then from this, we design the stencil DAG, and actually today, this is work that was finished a couple of weeks ago, but today, basically as of a couple of days ago, we can run this through Grid Tools with the support of CSCS. Grid Tools is a framework that is a Python framework, so GT4Py, that is actually used by climate scientists. And ECMWF is looking at it, the Meteo Swiss is looking at it, and even several groups in the United States are looking at using Grid Tools to implement their climate codes. So we can now take Grid Tools input, compile it to Dace, and then eventually compile it also to FPGAs if we wanted to. So we are hoping that this will be kind of a standardization for the climate community because it is a very convenient format to them, for them to work with, and also a convenient format for the performance engineer to optimize the code. So this is somewhat of the goal. But now moving forward with TensorFlow. So TensorFlow then performs an abstract hardware mapping where the idea is that we are reusing the buffers as well as introducing delay buffers for stencil computations. So I'll go into detail in this in a minute, but the message is, the main message here is that by design in our framework, we are using reading every memory location exactly once. So we are essentially IO optimal. For each single stencil. So for stencil chains, it gets more complicated, but for each stencil, we are IO optimal. And I want to show you a little bit, describe you a little bit how we can do this. Most CPU and GPU codes are not IO optimal. They have to read boundary elements multiple times. So we do this for a normal stencil by basically exploiting the fact that we can read these elements one by one. So if you're now looking at this very simple stencil here that produces this element but reads north, south, east, and west elements, what we do is we have some kind of a snake here. So we have 2 lines buffered, as you can see, or 2 lines plus 1 element buffered. So as the stencil moves, and I have an animation for this here. So stencil moves through this. As it moves forward, we can retire that element from our queue, so we can drop it from the queue, and we have to load that next element. So essentially all the gray pieces here, the dark gray pieces, are streamed in, while all the white pieces are retired. So we always have a constant size window into this, into the stencil, which is really great in the sense that we can actually live up to our promise to read every single element exactly once. So this is how it works. So for 2-dimensional stencils, we buffer rows, 2 rows plus 1 element, as I've shown in the previous one. For 3-dimensional stencils, we would need to buffer slices, right? So it's very much the same idea. And in general, for k-dimensional stencils, we would need to buffer k-1 dimensional objects. So as the dimensionality goes up, it's probably questionable that we can fit this on a single FPGA. But in weather and climate, these stencils are almost always 2-dimensional or even 1-dimensional. So that really fits well, even though we have so many of those that they still don't fit on today's devices. But every cell is essentially used by a stencil operation read exactly once. Right? So this is the fundamental principle, so IO optimality. But now there's an additional problem that we may have, and this is the global reuse. So we want to stream in from the array D here, or from the field D, to produce stencil A and to produce stencil C. right? So this field D is used by multiple different stencils at multiple different stages of the pipeline. A is earlier than C, right? Because A delays the input to C. Furthermore, to make this a little bit more complicated, the result of the A stencil is now read by a stencil, an operation producing stencil B, field B, I apologize, that is then later used to produce stencils, produce field C. So that is a complex case, but that case is actually extracted from real code, so that's not artificial at all. So these codes get extremely complex. So what we have to do is we have to exploit this reuse by streaming the data through the on-chip memory. So somehow we need to read D only once and use it twice for A and C. And we also need to produce A only once and use it twice for B and C. Right? So that's the important piece here. How do we do this? We do this with delay buffers. Here's exactly the same problem, a little bit more schematic. What happens here is we have the stencils A, B, and C producing the fields A, B, and C. So we have, of course, buffers at each of those stencils, as I mentioned at the beginning of my talk. So we have 2 input buffers for B. We only consider the left. Well, we need A of 0 and A of 1. We have 2 input buffers for C. And now we have the elements from A streaming in. So at the first step, the element would basically stream into this buffer in B and this buffer in C. And now the next element would stream in. It would go into this buffer in B, which is great. But unfortunately, this buffer in C is full. And this is still empty because B can only produce once both of the input elements arrive. So there's nothing happening here. There's nothing happening here. And unfortunately, this prevents C from consuming this A, which would free up the element from consuming A0, which would free up the buffer for A1. So somehow we have a deadlock case now, right? So because there's not enough buffering. So what we do in this case is very, very simple. And this is what the framework does automatically. The framework introduces so-called delay buffers. So we now need to have an additional buffer in the path that just buffers A1 for the period of time that B requires in order to compute its output. Right? So this is what the delay buffers do. So now the B0 arrives, and now it can consume the next element because now C is enabled to do its thing. Right? So perfect. So now we have no deadlock and both paths stream simultaneously. Of course, these delay buffers, they could require substantial memory for this buffering, substantial VRAM on chip, block RAM. Okay, but this is what we have to do in order to enable this full streaming. So this really, the size of the delay buffers depends on the internal buffer size of the elements, the parallel elements, and the pipeline depth, essentially. So this is automatic. Then we move this, once we have computed all the delay buffers, we move this into Dace. And on Dace, we basically work with these stateful data flow graphs that I mentioned before as an intermediate representation. So here we see another one. We have producing, here we have another read element that reads from DRAM. Here we have a write element that writes to DRAM. Here we have 4 different stencils that are chained. You can see the input-output names here are matching. I don't want to go too much into detail. And this can now already be generated as code to the FPGA. But now the question is, each of these stencils we can actually now optimize in some sense for parallel execution, right? So this is because we have them in the same state. Also, the disjoint stencils now map to parallel operations, as I just mentioned, because there is no data flow between them. The data flow is indirect through the pipelining, as you see through the names, but still they can be instantiated at the same time, essentially. So this is where the parallelism comes from. But now the question is, each of these stencils could be relatively complex. Like if you look at one of those, we see here, for example, this is the code that implements this stencil. Here we see the dependency specification, but the code is already quite complex. So can we now define a good processing element manually for Intel or Xilinx, for example, to implement exactly that stencil? And yes, we can. We do this through library node expansion. We basically say, well, we have this library node. We could just generate the standard code, or we could go ahead and plug in a hand-optimized code if we wanted to for that particular target FPGA as a library node expansion. So for example, here for the Intel FPGA, we replace these 4 nodes, these 4 library nodes with more complex versions of themselves. And here I want to use the opportunity to thank PC Square for the access to the Noctua cluster, which is where we develop these Intel FPGA these Intel FPGA tools and codes that you will see in the remainder of this talk. So thank you very much, Christian and Tobias and folks. Okay, so here we now have the expanded version. I don't want to go into too much detail. It's using Intel's channels and all of the specifics from the Intel architecture. But at the end, we can generate perfectly nested, fully pipelined loops, which is very, very important. And we can exploit these architecture-specific features, for example, shift registers. And the code that is generated, and this is just a small excerpt of the code, is code you don't really want to write manually. Just computing these indices here correctly will probably introduce several errors and at least cost you a lot of time and mental energy to make this happen. So this is all fully automated. So now, after we've basically covered the code generation pipeline, how this works step by step in Dace, I want to look at some performance results. And I want to start with very, very simple iterative stencils. So these are usually the stencils that people use for micro benchmarks. I have never seen them in a real application, but since this is the state of the art, we like to compare to those. We run this all in the Bitware 520N. This is exactly what's built in the Noctua cluster. The nice feature of this architecture is that it actually has 4x40 gigabit links of the FPGA connected through fiber optics to other FPGAs. And it's supported through the OpenCL channels that we can program those. So what we can do here is what we do here on the x-axis, let me explain this first, is we are chaining more and more stencils. So here we are increasing the number of chain stencils. So from a single stencil instance, 2 instances, and so on. So this is essentially tiling in time what we are doing here for a single node. And then of course we just exceed the size, or we don't exceed, but we are limited by the available logic on that node, obviously, if you have a spatial device up to a certain size. But what we can do then is we can actually go to 2 FPGAs and now go from 3,000 operations per cycle to 6,000 operations per cycle by just connecting these 2 FPGAs or 4 FPGAs, or in the Noctua cluster, even 8 FPGAs. And as you see, it scales perfectly, like 568, 1100, 2200, and 4200 approximately. So not really perfectly, but more than 95% efficiency. So we achieve this by using the streaming messaging interface that was published at Supercomputing 2019, a project that was run by one of my postdocs, Tiziano De Matteis. And the idea is really to have an MPI-like interface for FPGAs, specifically OpenCL. So it really looks like MPI, it programs itself like MPI, and we added it to Dace itself to have support here, and it's relatively simple for communicating streams. Of course, it's very different from MPI because it doesn't communicate messages, it communicates elements in the pre-setup channel. This was one of the things that Tobias was mentioning yesterday in the panel. I really enjoyed that discussion. So he was calling for standardization, so we could use this as a starting point even for standardization if we wanted to. Okay, so now looking at the actual performance here is relatively good. We have a comparison point to a hand-tuned version. So let us just look at the Diffusion 2D experiment. So Jacobi 3D is a very simple stencil. Diffusion is a little bit more complex. So we are comparing to Zuhuri et al., who has manually tuned for the exact same architecture. Has manually tuned OpenCL code to achieve 900 something gigaops per second. Our automatically generated code with a vector width of 8 achieves a little bit more performance and a little bit better utilization of the FPGA. So this is quite a good result. And essentially, this is all running through Python, right? Just to remind you, this is not manually tuned OpenCL code, which you cannot reuse for anything else, but this is code-generated code from a high-level specification as of TensorFlow. But now the question is, these diffusion stencils and Jacobi stencils are not too realistic because you can time tile them until the end of time. In real applications, this is very rare that you can actually do this. For these weather applications, the stencils are as complex as those. And now how do we get to real weather applications? Well, we use an example of a stencil chain, which now contains multiple stencils, that is called horizontal diffusion, that we got from our friends at Meteo Swiss. It's still a small example, but this small example is already large. You see the ... down there, and the ... indicates that this is a lot of additional code coming there. So Again, now we actually don't need the stencil definition. We can do this through grid tools in collaboration with CSCS pretty much automatically from the domain scientist specification. So we are hoping that we can release this soon as well. But the stencil chain, this horizontal diffusion stencil, is really shown here. We have multiple the three-dimensional inputs, the blue circles here. We have multiple one-dimensional inputs, the gray circles. We have multiple stencils. We have multiple outputs. And so this is the DAG automatically generated. Performs more than 130 floating point operations per grid point, per output grid point, including complex ones like SQRT, square root, minimum, maximum, which is great for FPGAs, right? You can just synthesize as many square root units as we need, or minimum, maximum units are nearly trivial on the FPGA. We can even pack multiple of those in the same clock cycle. And we can also support data-dependent branches. So this checks all the boxes for FPGA lovers, right? So data-dependent boxes, branches, we just synthesize it twice if we have enough space, and then there is no branch penalty whatsoever. It just flows through the right side. And so we get to an arithmetic intensity of 65 operations per byte here. So, but now let's look at the real performance. And the real performance is on the Stratix 10, as I mentioned before, again, the Noctua cluster. So we get 145 gigaops per second. And this FPGA has a peak bandwidth of 77 gigabyte per second. We achieve 52% of that peak bandwidth. All of the results I'm going to show are memory bound, so the roofline percentage is always relative to the peak memory bandwidth, which I'm showing in the previous column here. So now if we compare this to the Xeon 12-core machine, we're using all 12 cores. By the way, this code is highly tuned code coming from the Dawn framework, which is Meteo Swiss's prototype, highly tuned implementation for their own codes. So this is gives very respectable performance. This machine has a peak bandwidth of about the same, but a much lower utilization because the memory access is quite complex for these. Here we can generate memory access controllers that stream it very nicely. Here in the CPU case, we need to load these cache lines, and it's quite problematic. So we only get 32 gigaops per second. So we are much faster than a 12-core Xeon, highly tuned, which is quite nice. But now if you're actually comparing this to GPUs, to the devices that are used in practice, at least in Switzerland for this kind of weather forecasting, we see that we are slower even than the P100 and significantly slower than the V100. But we can also see that their utilization is much worse than ours. So a factor of 2 away, but they have a more than 10 times higher baseline bandwidth. They have HBM, they're incredibly expensive. And also from the technology node they're manufactured in, the Stratix 10 is somewhere between the P100 and V100. So that is actually already better than the P100, even with the nearly competitive, even with the 10 times lower memory bandwidth. You can also see that NVIDIA fixed a whole lot of things, partially based on our feedback, to improve the memory subsystem to load for these very small stencils. By the way, one of these problems with the weather codes is that the stencils are extremely small. There are 32 by 32 elements for each piece, because you need to run in a certain time to predict the weather for tomorrow. So they need to run very fast, and thus they are always in the strong scaling regime. But now, as I mentioned, we are memory bandwidth bound, and it's an unfair comparison to compare a device with 77 gigabytes with a device of 100 gigabyte per second, right? So let us eliminate that bound. And so we synthesized our FPGA design just working on dummy data, not reading from DRAM, but just generating the data in the FPGA itself, and see how much the FPGA itself, the logic, could deliver in operations per second. And we see we beat the P100 hands down. And we get reasonably competitive with the V100. So I would predict that in the same process, because Stratix 10 is about somewhere in between, they may actually be about the same performance. So with a significantly lower or slower memory bandwidth, because our utilization is higher. But that would need to be shown. So that's an experiment we can't do. Our conclusion, we run this at 318 megahertz, so also no comparison to the 1.5 gigahertz of the CPU at 48% DSP utilization. So really, Stratix 10 today has insufficient bandwidth, but FPGAs are quite a good target for this if you can pipeline parallelize all of these things, and if you had the right architecture surrounding the FPGA. We do have a Xilinx HBM device in-house, and we are working with it currently to achieve higher bandwidths on the real device. So by the way, the stencil flow is fully reproducible. We invite you to break it. Please try it, download it. There's a GitHub page down here that you can just use. It should run without any trouble on the Noctua device, on the Noctua cluster. Actually, it was reproduced by an independent party to really down to the results on that cluster. So the dream now, what's with this dream, right? I mentioned we wanted to run a full climate and weather code on FPGAs. So we haven't achieved this yet. We are on the road towards it. But the question is now, is this realistic? Our friends at ECMWF were actually launching a study what it would take to run a digital twin of the whole Earth at high resolution, so 1 kilometer resolution essentially. And this is of course one of those HPC problems that is humongously big. You need a dedicated supercomputer for this with tens of thousands of devices. So the conclusion, or one of the conclusions of this study, was that today GPUs look like the most encouraging option, and the proposal there is about 20,000 GPUs with a 20 megawatt total power. We could run a live simulation of the Earth as a digital twin, as the Earth is advancing. We could also run a faster simulation to understand our impact on the CO2 emissions, for example. But you can read this all yourself in the Nature article that was led by ECMWF, The Digital Revolution of Earth System Sciences, where the idea is really to have a digital twin of the Earth and really understand what the human impact on the climate is and how we can change policy in order to mitigate that impact, or even predict micro events like floods and severe thunderstorms at a higher resolution or a higher lead time than we do it today. So Dace is a very versatile platform. I just talked about a very small subset here about this NumPy, but really if you have a favorite language, please contribute it. We are always accepting pull requests. Also the backends are versatile, so we have everything ranging from NVIDIA GPUs, AMD GPUs. I didn't talk about GPU at all. CPUs, also ARMS SVE. I talked about Intel and Xilinx FPGAs. We will soon have an RTL backend. And then your favorite processor can be added again by yourself or in collaboration with us. We accept pull requests, so please support us. So the last case I want to mention, or the last piece, is really Dace also works at very large scale supercomputers. Here, the top one machine in 2019, the Summit machine, a code that was generated with the help of Dace was actually awarded the Gordon Bell Prize in 2019 as kind of the largest scientifically relevant or the fastest scientifically relevant code running there. There are other talks online if you want to look at the details there. Currently, we're working on deep learning, climate codes, and Green's function solvers together with Mathieu Levisier. Climate is together with ECMWF, Vulkan, Oliver Foro, and CSCS, of course. And deep learning is in a collaboration with various industries. So try Dace, pip install Dace, run it yourself. Let us know if something goes wrong. There's a Stack Overflow channel where you can post questions. So with that, I would like to summarize my talk. So what have I really said? I've talked about high performance computing really being a data management challenge. I've talked about how we believe this could be addressed by separating the concerns of the domain scientist, the performance engineer, and the code generator, and each of those adding an order of magnitude more lines of code, of course, if you want to generate fast code. I talked about NumPy Bench to inspire you to either play with these things yourself or contribute benchmarks where you believe these patterns should be supported in frameworks like Numba or Dace. And then I've zoomed into the hardware design. So how do we generate hardware descriptions? This is mainly run by my student Johannes in collaboration with Tiziano. And the Stencil Flow paper, particular work, particular detail that we figured out. And then actually trying to see how this could apply to real weather codes, where we are looking forward to work with this right now. So then thank you very much, and I'm open for questions.